So this is going to be a 4-week unit. Okay, it will take us all the way up to winter break. Okay, ideally, the way I have it planned right now is, and this is all loosey-goosey too. Right now, I have it planned that we'll take a test on that Tuesday of that last week, because then Wednesday you don't have classes, and then Thursday that gives us a day that if we would perchance have an ice day or a snow day or a cold day or who knows what kind of a day, we have that to play with. And if we don't have any of those things, which I don't expect we will because it's 41 degrees and raining outside, that we can do an extra credit type project on that day. So that's out there. So all right. So today we're going to start rational functions, and the goal is to graph rational functions. Okay, that's our goal. That's our end game in mind. Is we want to graph all kinds of rational functions. Now you graphed a little bit of them last year in Algebra 2. So most of this stuff should be review up until we get to the point of some higher level type stuff, which we'll get to next week. Okay. There will be a quiz this week Friday. There will be a formative this week Wednesday. Okay. So formative on Wednesday, quiz on Friday. Okay. I strongly recommend that you have a note card out, because I will be basically telling you what to put on your note card this chapter. Okay, your note card production kind of has slacked off, and I haven't crunched the numbers yet, but I will crunch the numbers probably tonight. And the note card, the scores on the note card versus scores on the note card are better, but they're still not good. They're not a whole lot better from those that did it on the note card and those that didn't use a note card. So yeah, it's starting to get a little frustrating with because you guys have a note card, so your scores should be elevated, but they're not. So I'm going to take some more ownership in the whole note card issue. Okay. So rational numbers. What's a rational number? Numbers that can be written in the form of what? Yeah, exactly. They're numbers that can be written in the form of a fraction. Okay. If you think about the word rational, notice what's in rational. The word ratio, which is a comparison of two things, okay, usually given to us in fractional form. Okay, so a rational number is a number that can be written as a fraction. Now, let's fast forward that to rational fractions, or rational functions, excuse me. A rational function, f of x equals p of x divided by q of x, where p of x and q of x are polynomials, and q of x is the zero polynomial. It's not the zero polynomial. So a lot of stuff going on in that sentence. So let's break it down a little bit. Let's start at the end and work our way back to the beginning. So q of x is not the zero polynomial. What do you think that's going to mean? Can't have 0 in the denominator because we can't divide by 0. So q of x can't equal 0. Because if we're equaling 0, then we're dividing by 0, and that's just not right. Okay? P of x and q of x are polynomials. What does that mean? What's a polynomial? What do you think a polynomial is? Give me an example of one if you can't think of how to describe it. Don't everybody speak at once. Give me an example of a polynomial. Monty, how old are you? 17. 17 is a polynomial. What? It's a function. Okay. So give me an example of one.
F of x equals x cubed plus 5x squared minus 3x plus 2.
Okay. So 17 is a polynomial, and x cubed plus 5x squared minus whatever is a polynomial. What's a polynomial?
Something that has zeros?
Nope. 3 words. I can name a polynomial in 3 words. Multi-termed expression. Okay. A polynomial is an expression with terms, would be another way to say it in 3 words. Okay? All right? So if P of x is an expression with terms, and Q of x is an expression with terms, but not equal to 0, give me an example of a polynomial function. We'll call it f of x. Give me an example of a polynomial function. Birthday. How many brothers and sisters do you have? 2?
They're all 1.
How many people in your family? Is that a rational function? Does it have a polynomial for a numerator? Does it have a polynomial for a denominator? Is the denominator 0? No. So it's a rational function.
So do we have to write out, because, that's not 0, but...
We'll get there. I know what you're thinking about. We'll get there. That's this part down here.
Okay.
Yeah, we'll get there. Okay? Yeah. We're just making some. Now, we could get much more complicated, right? We could go, let's go g of x is equal to 7x to the 5th minus 4x to the 4th plus 13x squared minus 14x plus 42. My fingers are going faster than my mouth is going. All over 17x to the 18th power minus 62x to the 13th power plus I like 73x minus 1. Huh? Is that a rational function? Yeah. It's a fraction. It's got a polynomial for a numerator. It's got a polynomial for a denominator. Okay? All right? So, the domain of a rational function, we were talking domains here in chapter 6, the one that we just got through doing. Okay? The domain of a rational function includes all real numbers except x values which make the denominator equal to 0, which is what you were asking about before, Shante. Okay? So we don't like denominators equal to 0, so we can't have those as part of the domain. So we start with the domain as all real numbers, but then we pick out what makes the denominator be 0. Now, the nice thing is, in the last chapter, we had to deal with radicals and we had to deal with denominators equal to 0. In this chapter, we just have to deal with denominators equaling 0. You don't have any radicals to deal with in this chapter. Okay? Fear not, it's at the top of this slide too. Okay? Right? So, what happens at those spots where the denominator is equal to 0? So, let's start with a function. Let's go pretty basic here. F of x equals 7 over x minus 2. Okay? Rational function. It's in the form of a fraction. It has a polynomial numerator, polynomial denominator. Okay? So, the domain of this function is going to be all real numbers with the exception of what? X cannot equal 2. So my question is, what happens at x equals 2? Okay. Because I can't put 2 into my function. Okay. So what happens there is something called a vertical asymptote. Okay. A vertical asymptote is a couple of things. First off, it is a line that the function does not exist there. Right? The function doesn't exist at x equals 2 because I'm dividing by 0 at x equals 2. So my function doesn't exist at all there. Okay? And second, this one's very important, the function cannot cross the vertical asymptote. Highlight that in your notes. Okay? Your function cannot cross a vertical asymptote. Okay? Cannot. Okay? Now, it's a line. It's a vertical line. So it has to come in a certain form. Okay? Remember that vertical lines are in the form x equals some number. So since this is a vertical line, it's going to be a vertical asymptote is going to be x equals some number. Okay? So in the domain, we would write it like this. To write out a vertical asymptote, we would write it as x equals 2. Okay? Because it's not just 2. 2 is a number. Vertical asymptotes are lines. They're vertical lines. So we have to write it out correctly. Okay? Now, it's going to go on the graph too, and it's going to go on the graph as a dashed line. Solid lines or solid curves are spots where the function exists at. Okay? This, our function doesn't exist at, so it has to go on your graph as a dashed line. It also must be on the graph. One of the reasons that we're not going to be using graphing calculators at all for the next month is because when you graph this function on the graphing calculator, it doesn't give you the vertical asymptote. Okay? It doesn't have that capability yet. It doesn't give you the horizontal asymptote. It doesn't give you the slant asymptote. It doesn't give you any of those. It doesn't even give you the hole if there's a hole. Okay? So that's why we're not going to be using graphing calculators at all in this unit. Okay? And the last thing, by the way, if you hadn't noticed, I shortened up vertical asymptote into VA. Okay? The VAs are found from the restrictions of the domain. And notice, all you do to go from the restrictions of your domain to the vertical asymptote is you get rid of the slash through the equal sign. Okay? Alright? Now, if this were like, if my domain had restrictions of plus or minus 3, okay, which is possible, right? Okay, I would write those out separately. I would not write my vertical asymptote as x equals plus or minus 3. I'd write it out as x equals negative 3 and x equals positive 3. I'd write it out as 2 separate lines to signify that it's 2 separate lines that have to go on my graph. Okay? All right? But we'll get more into that as we go along. Okay? So, on your note card, for sure, we're going to have, in the end, by the end of this unit, you're going to have 8 steps. Okay? That are going to be on one side of your note card. You're going to reserve one side of your note card for just the steps. Okay? So the first step, then, is step number 1. It is find the domain and any vertical asymptotes. By the way, I forgot to mention too, let me take this down a little bit. I forgot to mention too that there can be multiple vertical asymptotes. Okay. Whatever the degree is of your denominator, that's how many vertical asymptotes there are. Okay. All right. Let's put this to work now. So, our first example says. Find the domain, use logic to describe asymptotal behavior, what the function is doing near the asymptote, and end behavior. And we'll get to all those when we get there. So first off, let's start with our function. Our function is f of x equals 1 over x. Okay? What is the domain of that function? All real numbers, except x cannot equal 0. Okay? From my function, I take the denominator and I set it not equal to 0 and then solve it. In this case, it was already done for us because it was just 1 over x. Okay? So, that means then that if that's my domain, what then is my vertical asymptote? X equals 0 is my vertical asymptote. Okay? Alright? With me? Now, in order to figure out asymptotal behavior and end behavior, we're going to need to use logic. You're going to have to think this week. I know. I'm the meanest math teacher you have. Okay? So, let's go through some logic before we come back to that. Okay? So if I have what's called fraction logic, if I take some number, I don't care what that number is, and I divide it by a ginormously huge number, okay? So basically I'm taking some number and dividing it by infinity. For some reason, it doesn't like the... Ay, caramba. Oh well, looks like we're going to have to live with it. Okay? So we're going to basically take some number that I tried 3 times. I'm sorry. Okay? We're going to basically be dividing it by some ginormous number. Let's call it infinity. Okay? So, logically speaking, if I take 1 and I divide it by 1, what do I get? 1. If I take 1 and divide it by 10, 0.1, right? Okay. If I take 1 and divide it by 100, 0.01, what's happening to my value? Getting smaller and smaller and smaller, right? Okay. So if I take 1 and divide it by 1,000,000, 0.000001, right? Okay, really small. Okay, logically, will that number, what does it get closer and closer and closer to? Get closer and closer to what? 0. It goes to 0. Now, here's where we blow minds. Does it ever get to 0? No, it never gets there, but it's just infinitely close to 0. Okay? Never gets there, but it goes there. Okay? So if you take a number and you divide it by a ginormously bigger number, it's going to go to 0. Okay? Let's flip that around. Let's take some number and divide it by a ginormously small number. Okay? So now I'm taking some number and dividing it by 0. Basically by 0. Okay? Because I can never divide actually by 0, right? Okay? So now let's take some number. So let's go 1 again. 1 divided by that 1,000,000. 0.00000001. What do we get? We get 1,000,000, right? So what happens to that result? It gets huge, right? Okay. What does it go to? As I get smaller and smaller and smaller, that number down here that I'm dividing by, it's going to go to infinity. Okay. So dividing by a super huge number sends it to infinity. Dividing by a super small number, dividing by a super huge number sends it to 0. Dividing by a super small number sends it to infinity. Okay? Now, let's put that into play here. So, I need to talk about my end behavior. Okay? So, end behavior says, as x goes to positive infinity, my function goes to something. Right? Okay? So as x goes to infinity, positive infinity, is that super big or super small? Super big, right? So we've got 1 divided by a super huge number. Correct? Okay? So what's that going to be? 1 divided by a positive huge number. It's going to be close to 0, right? So it's going to go to 0 from above. And that's how we write it. It's going to be on the positive side because it's positive 1 divided by positive infinity. It's going to go to 0 from above. So my function is going to be above the x-axis, but right on it. Okay? As x goes to negative infinity, what's my function going to go to? 0 from below, right? Because now I've got positive 1 divided by a negative ginormous number. Okay? So that's going to go 0 from below. So there's my end behavior. Okay? Now, here comes the funkiness. Now we've got asymptotal behavior. My asymptote was x equals 0, right? So now I'm going to talk about what my function is doing as x goes to 0 from the left. Okay? So as x gets closer and closer to 0 from the left, I'm negative, right? Right? It's negative. So 1 divided by a negative small number is going to be what? Using our fraction logic. Because that fraction, or that number is going to get smaller and smaller and smaller the more I walk in from the left towards 0. What's the answer? Using my fraction logic, as x gets closer and closer to 0 from the left, so where's my function going? So where is it going? Negative infinity? Yes? Okay. And then as x approaches 0 from the right, what's my function doing? It's going to where? Which one? Positive, because now I'm on the positive side of 0, and as I get closer and closer, that number is going to be a small number, but it won't ever be 0, so I'm going to positive infinity. Okay?
What does that look like?
What does it look like?
Yeah.
So what does this function look like?
Yeah, 'cause
So if we were to graph this function, we basically, just by finding those 4, we basically graph the function. Okay? Later on in this chapter, okay, you're going to get all this stuff right off of the graph. We're going to start graphing on Thursday, so we won't have to use as much logic to go through this, because you'll just say, oh, well, as this is going to here, and this is going here, and all that fun stuff. Okay? But so basically what's happening here is you've got a vertical asymptote there, okay, and your function is here and here. Okay? So we basically graphed it, but we'll get into the steps on how to graph it later on. Okay? Alright? So, you now try that one. Okay? Find the domain, use logic to describe the asymptotal and end behavior. What's the domain? X equal what? 4. Okay. So all real numbers, with the exception x, cannot equal positive 4. Okay. What does that mean for vertical asymptotes? X equals 4 is the vertical asymptote. Okay. So, end behavior then first element of end behavior. As x approaches positive infinity, 0 from above. So what you're saying is, as x approaches positive infinity, f of x, and check the title, approaches 0 from above. Agree? Disagree?
Can you explain real quick what it is, or
Like, what do you mean?
Why is it plus or 0 from below? If it's going to take a while, then I can just put it on that.
Yeah. Agree? Yeah? Yeah? Okay. Big number, right? Because positive infinity is a big number. Okay? With me? Positive infinity, huge number. And I subtract 4 from it, still a pretty big number, right? 1 divided by a huge number is going to go to 0, but it's still going to be positive from above. Okay? Second element of end behavior. Go ahead, Cece. Okay, as x goes to negative infinity, goes to 0 from below, because now we're dividing by a negative huge number, and subtracting 4 just makes it even huger. Okay, so it goes to 0 from below. Positive 1 divided by negative is a negative number. Okay, so there's end behavior. Now we've got to deal with asymptotal behavior. First element of asymptotal behavior.
As x approaches 0 from the left,
No,
right,
no, no. No. It starts with as. He had that part right. As x, go ahead, David, approaches. No.
oh, 4.
As x approaches 4. 4 is my asymptote. Okay? X equals 4 is my asymptote.
Why don't you do it on the top?
Because that's f.
Okay.
Yeah. That's my function. Over here it's my asymptote. So I gotta go to my asymptote. Okay? So as x approaches 4 from the left. Oops, that's comma. What does my function do? Goes to positive infinity? Negative infinity. We got some issues here. We got two differing ones. So let's think about this as, okay, as there's 4, right? Okay, so I'm approaching 4 from the left. Give me a number really close to 4, but to the left of it. 3.9, we'll say. Okay, for lack of a better term. 3.9, right? Okay, I put 3.9 into my function. 3.9 minus 4 is going to be a small number, but what kind of small number? It's going to be negative. Okay, because it's 3.9 minus 4. So positive 1 divided by a negative small number is going to go to, it's going to be negative, right? And it's going to go to negative infinity. Flip it over. now we're coming from the right. So as x approaches 4 from the right, what does my function do? Because now if we think of like 4.1, right? It's on the right side of 4. Okay? 4.1 minus 4 is going to be positive. Small number. 1 divided by a positive small number is going to go to positive infinity. Okay? I cannot stress fraction logic enough. Okay? It will simplify your lives to do this. Okay? Because it gives you a great check when we actually get into graphing these on Thursday. Okay? With me? Now, homework is going to be tricky in this section. Okay? The reason being, there's not a lot of problems in your textbook that I can rely on. So we're actually going to be out of the textbook on this one. So your homework for tonight is to do this problem. Okay? Not only will you do this problem, actually you'll do it right now, but then your homework tonight is to go on to It's Learning, since hardly anybody's going on to It's Learning, because I can see who goes on and who doesn't go on. Okay? Your homework then is to go on to It's Learning sometime after 3 o'clock today and before school tomorrow and check out the answer. Okay? Because I'll know if you went on it or not. Okay? Because it's time stamped as to when you guys go on.
So are we gonna be turning this in, or can I put it right in the
You can put it right in your notes. Yep. Because your homework is not actually turning something in. I'm going to log on to my computer tomorrow morning at 7:45, and I'm going to see who went in. You know what I mean?
So we go in and do what?
Check out the answer.
Oh,
Make sure you did it right.